Right, day 17. Secure coding again, filtering for order amidst chaos. After handling unrestricted file uploads and SQL injection vulnerabilities, McSkidy has continued to review Santa's web applications. She stumbled upon a user-submitted input that is unrecognizable. Some are even bordering on malicious. She then discovered that Santa's team hadn't updated these web applications in a long time, as there clearly needed more controls to filter misuse. Can you help McSkidy research and learn a useful technique to handle that in the future? At this point, we're already well aware of security concerns regarding input validation and analogous. How the fuck? Analogous. I can't speak today, right. To being a castle wall of your application that forms the first line of defense against an array of scenarios from harmful misuse to outright malicious intent. Validating input merits the same effort as its medieval counterpart in terms of its hardening. I've lost where I am. Okay. It goes without question that insufficient effort in this space may result in attack vectors being vulnerable and consequently exploited in your application. Day 15 talked about input validation in light of unrestricted file upload. Day 16 focused on SQL injection. In this task, we'll be exploring input validation in a more general sense before touching upon one of its most complex use cases, free-form text fields, followed by a quick discussion on how you may move forwards in your secure coding journey beyond input validation. So, generally, an effective way to validate input is first to know how a specific piece of data is going to be processed by the rest of your application. The Day 15 task is a beautiful example that shows more or less the mindset required to be able to effectively tackle the specific case of unrestricted file upload. Data then goes through syntax and semantic validation checks to ensure that the user-provided values are both proper in their syntax. The answer follows the proper context asked by the question, and the logical value, so the value makes sense for the question. Going back to Day 15, you cannot manually type your CV into the input field. The form asks for a file, so that it's simply not what's being asked. You cannot just upload any file, it should follow a set of very specific rules, the implementation of which was all discussed in the latter parts of that task. Then comes whitelisting, where you can be very specific with what your forms will accept and immediately strip or even drop ones that don't fit the predefined allowed category. HTML5 and regex. So HTML5 has a built-in feature with lots of help for validation and user-provided input, minimizing the need to rely on JavaScript to achieve the same objective. The input element specifically has an array of very helpful capabilities centered around form validation. For instance, the input type, which can be set to specifically filter for an email, a URL, or even a file, among others, promptly checks whether or not the user-provided input fits the type of data that the form is asking for, and so it will feedback based on its validity. This is immediately returned to the user as a result. For even more granular control of input being provided, regular expressions can be integrated into the mix. Simply use the pattern attribute within the input element and you're all set. Here is a nice resource to help you get started with regular expressions. A couple of examples are shown below. So that input for a username, the pattern has to match A to Z lowercase and A to Z uppercase with 0 to 9 characters, and then one or more of those. So it could be anything with this character set one or more times. Then this one, the pattern has to be anything one or more times at tryhackme.com. The pattern in the first line of code above is easily one of the most foundational regular expressions the patterns can use. The instruction here is to match any of the strings specifically comprised of only letters and numbers. an alphanumeric pattern that is case insensitive. The pattern in the second line is a bit more pointed in its instructions, saying it should only be characters that end with tryhackme.com. Developing regular expressions can be very daunting as its nature is complex, however its capability to match very specific patterns is what makes it special. Well-built regular expressions introduce a great way to immediately filter out user-provided input that doesn't fit specific requirements that you have set. This song's really bizarre. 1, 2, 8. There we go. So regex 101. This section will talk about some regex tips to help you get started. Match any lowercase character from the English alphabet. The pattern is A to Z. That's a lowercase a to Z. We can deconstruct it as so. Square brackets indicate you're trying to match one character within a set of characters inside the brackets. For example, we're trying to match any vowel with the English language. We construct our regex as follows: A, E, I, O, U within square brackets. The order of the characters doesn't matter, and it will all match the same. Square brackets can also accept a range of characters by adding a hyphen, as seen in our original example. You can also mix and match sets of characters within the brackets. This means that you want to match any character from the English alphabet regardless of case, because it's got A to Z of both upper and lowercase. While A to Z 09 means that you'll want to match only lowercase alphanumeric characters because you've excluded the uppercase A to Z. We also need to talk about regular regex operators. One of the simplest is the wildcard operator, denoted by the dot. This means that regex will match any character, and it's quite powerful when used with operators like star and plus and min and max. The asterisk or star operator is used when you don't care if the preceding token matches anything or not, while the plus operator is used when you want to make sure it matches at least once. Curly brace operators, on the other hand, specify a specific number of characters that you want to match. To match the string that's alphanumeric and case sensitive, our pattern would be A to Z again uppercase, and 0 to 9 plus. Plus operator means that we want to match a string. We don't care how long it is, as long as it's comprised of at least one letter and number of A to Z, uppercase A to Z, or 0 to 9. So, a better example, let's just do regex 101. Surprised they haven't got this in the example. So regex 101, this resource is amazing, by the way. So, just going to copy this. So, I put my expression here. And I can say A in the test, so it matches A, it will match A. If I had something that isn't an A to Z, like, or isn't an A to Z or a number, so if I do hyphen A, it only matches the A's, it doesn't match the hyphen. If we want to ensure that the first part of the string is comprised of letters and we want to match it regardless of if there's numbers after, we would use, so there's a caret, A to Z plus, so we want to match one or more A to Z characters at the start of a string, and then 0 to 9 is like any numbers at the end afterwards. Should say here, so the caret and dollar operators are called anchors. This denotes the start and end of a string, so caret's the start, dollar's the end. Since we wanted to ensure the start of the string is comprised only of letters, adding the caret is required. If we want to match just the lowercase letters, then there are between 3 and 9 characters, we would do that. So here we go. So this is beep. So the start of the string must be an A. If I keep adding A's until there's 9, it will stop matching. So there we go. So A doesn't match on its own, AA doesn't match, AAA, so now we have 3, it does match, 4 matches, 5 matches, 6 matches, 7 matches, 8 and 9 matches, and as soon as we do 10 or 11, they don't match. So you can see how this is now only returning this section. Like, these are the matching inputs. Right, if we want strings that start with 3 letters followed by any 3 characters, our pattern would be this. So let's try that. So the only one that matches now is this center one, because the first 3 are A to Z, and then dot means anything, so anything that is at least 3 long. So everything at the start and end of the string can only be 6 characters long, so the only one that matches is the 6 A's in a row. There's also the concept of grouping and escaping, denoted by brackets and slash or forward slash. Grouping is done to manage the matching of specific parts of the regex better, while escaping is used so we can match strings that contain regex operators. Finally, there is the question mark operator, which is used to denote that the preceding token is optional. So let's look at the following example. If we want to match both tryhackme.com with a www dot in front and tryhackme.com, our pattern would be... Okay, so let's copy that. I need the examples, so let's copy those. So there's my input. So now they both match, and you see the green one, which has a grouping of www dot, that was captured optionally, so, but both of them match. The operator marks the start of the string, followed by the grouping, and www escaped will immediately followed by the question mark operator. The grouping allows the question mark operator to work its magic, matching both strings with or without the www dot at the beginning. Tryhackme/.com, the dollar operator marks the end of the string, preceded by the string tryhackme and the escaped dot, which is within the string.com. If we don't escape the dot, the regex engine will think that we want to match any character instead of just the dot on its own. So I can prove that again if I just take the escape off. Here it still matches, but if I copy the example, so now it would also match if I put like a hyphen, which obviously we don't want. We don't want a hyphen. So if I escape the dot again, it now will only match where there is a full stop and the hyphen gets excluded. So it's imperative to note that the wildcard operator can lead to laziness. It's and consequently misuse. As such, it's always better to use character sets through the brackets, especially when we're validating input that we want it to be perfect. Here's a table to summarize everything above. A unique case of freeform text. All of the techniques we've covered in this task thus far are mainly concerned with structured data that we already expect what it should look like. However, compared to the validation of structured data, free text is more complex and not straightforward. Structured data may have inherent characteristics that allow us to set them apart quite quickly. For example, names shouldn't consist of special characters, although some names have, they can be whitelisted. The age should only consist of numbers with an absolute maximum of 3 characters. You're not going to have a 1,000-year-old person. Syntax and semantic validation checks can be immediately done on them, and the chaos suddenly doesn't seem too bad. In contrast, Free text fields are more of a free-for-all, and so validation checks are more limited. The challenge of securing it is generally vaguer. Yet, like all great engineers before us, we power through these challenges and make the best of what we're given. Listed below are some considerations to ponder on. So first we'll start again with a question of how the piece data is going to be processed with the rest of the application. What will the context for which this freeform text field will be used? Free text fields for a blog post are tackled very differently than fields used for a small comment section. Is the free text field necessary for your business purpose in the first place, or could you just implement it differently and achieve the same goal? All these things are essential to know as part of writing a secure code and avoiding writing vulnerable ones. Then we go to the tricky part, since syntax and semantic checks are pretty much impossible due to the nature of a freeform text field. The best bet in having a bit of control through whitelisting. This OWASP cheat sheet lists down the general techniques to perform whitelisting and can be summarized below. Ensure that no invalid characters are present through proper encoding, and then whitelist expected characters and character sets. You should definitely check out the cheat sheet series, by the way, it's phenomenal. So this covers all of the things to do. I've gone past it now, there we go. Freeform Unicode text. Alright, so the best remediation tactic for the next part of the discussion, let's take a look at the simple base code below, where a programmer has attempted to retrieve the usual details from a user. So collecting name, birthday, email, age, favorite website, and then a random comment field. So this example is a bit bare and would have been an immediate nightmare, as it raises an alarm, not just in terms of security but also in terms of getting a ton of garbage responses. Since all of the text inputs by default, the birthday and age field may receive responses that aren't within a specific context. Furthermore, malicious users have free reign over the fields, essentially allowing them a playground to tinker with. In this case, if no input validation is done at all, let's fix it up and review it again. So we're taking our original input. The changes to the above are literally just the additions of the type attribute and their corresponding values within the input element. Yet there's already a world of differences between this one and the base implementation. Take note that security wasn't the main focus of these changes, yet it succeeds in mainly alleviating the chaos that the prior implementation would have otherwise invited. Going back to the discussion above, this example of syntax check was done in the HTML layer. However, the implementation above is still susceptible to misuse, especially for very naughty users, but let's fix that up and review it again. So all they've added is a required tag. They've given it a minimum length of 4, so the name must have 4 characters, up to 70 characters. We're then requiring a birthday within this date range. We're requiring an email that matches a regex. And we've set a maximum age of 122 and a minimum age of 8. So, yeah, so we've read that. These semantic checks should follow the proper business context to be effective. For example, the implementation above is geared towards TryHackMe staff, marked by the TryHackMe emails. Furthermore, applying the foundation of input validation not only ensures that the data being provided is proper, but it also drastically limits the attack surface of the input fields. This is the reason why we haven't touched the text area field at the very end of the code block. As discussed earlier, freeform text is unique in the way that it applies syntax and semantic checks. Pretty much impossible. In order to secure this one, we first need to define what content, characters, character sets, symbols, etc. are acceptable, and then perform the actual whitelisting. Even then it wouldn't be enough, and it's still a very open field. So techniques such as output escaping and using parameterized queries, among other things, should be implemented as well. Client side versus server side. So our discussion up to this point is geared towards the input validation to ensure that pieces of data that we're getting from the user are not garbage. Proper input validation on the client side limits the misuse and minimizes the attack surface of the application. However, that doesn't actively cover malicious use cases. As opposed to the above examples of validating input on the client side, output escaping and parameterized queries are implemented on the server side of the back end, adding computational load to the server but ultimately helping in the securing of the application as a whole. This is done as an exercise of inherent distrust of the user-provided input. The examples below use built-in HTML entities PHP function to escape any characters that can affect the application. On the other hand, the one below uses the HTML purifier library to help with some use cases such as our text area conundrum above. So both examples are done on the server side to escape characters and purify its content, both effective ways to prevent the user misuse and XSS attacks. Implementing both client and server side validations ensure that no stones have been left unturned. This exact case highlights the importance of layering our defenses and shows point blank the limitation of a client-side input validation. It also gives rise to the notion that the input validation is not a one-stop shop for securing your application. Specific cases warrant specific security requirements, and so on. This factor alone, it's already apparent that there exists multiple ways of attacking the challenge of securing user-provided input, and most of the time they're implemented on top of each other. Not all solutions are equal. Input validation is an important layer of security that all production-level applications should have. However, no matter of how perfect your input validation is for your specific use case, there simply are limitations to all kinds of security implementations, and input validation is not exempt from it. You cannot make your application fully SSH cross-site scripting proof through input validation alone. Controls must be put in place at the input level that lessen the attack surface of the application, but it doesn't fully remediate it. Full remediation of an XSS vulnerability in your application requires an additional layer of defense, such as mitigation on the browser level via secure cookies, content security policy headers, and escaping and purifying the user input provided. In light of these remediation techniques, it makes sense to tackle each challenge on its own. SQL and LDAP related vulnerabilities are addressed differently from cross-site scripting, so why try to fit them all with the same formula? So in summary, despite being a very important security control, due diligence in securing an application involving user-provided input shouldn't stop invalidating the input per se. As seen in the previous examples, user input may be valid, but it doesn't necessarily mean that it's harmless. There are a lot of tools and frameworks out there that used properly can help secure your application. For instance, HTML5's features can help in minimizing input form misuse, while their use of regular expressions can help filter out what we need from the user more granularly. If we take a closer look at regex here specifically because of the powerful capability to implement filters. While the above examples aren't directly concerned about application security, they help minimize the attack surface of the application, which is further tackled through server-side validation techniques such as output escaping and using parameterized query. We should be realistic and not try to solve all security problems with input validation. There is one control that could prevent persistent malicious actors, and so layering the controls is a better way to move forward. So the exercise for today is we've prepared a regex exercise that you can access through the machine provided. First, let's start the virtual machine by pressing the Start Machine button at the top of the task. The machine will start in split screen view in the case of the VM is not visible. Press the blue show split view button to see it. To practice your regex, first change the working directory to the regex practice folder using the command cd regex practice. Then you can use either egrep via the following syntax or the registry check py script written for you via Python. So let's start the box. Probably should have done that first. See if it pops out. Yeah, there we go. Cool. So we've got the side by side. We're aware that some structured data are more complex than others, so we've got a specific syntax you may follow to make the exercise simpler. Have fun. So you can filter for usernames, alphanumeric, minimum of 6 characters, maximum of 12 characters. May consist of upper and lowercase letters. If you're filtering for an email, the following form: local part at domain without quotes marks. Local part is a random string. The domain is in the form of domain name TLD. All top-level domains are .com. Filtering for URLs starts with either HTTP or HTTPS. Some of the URLs have www and the TLD shouldn't exist. So this is actually a regex challenge. This should be fucking bullshit. There's another good reason to have this, because I'm sure this is going to be friendlier than whatever it is they've got going on. Right, so change your working directory. So we should really go into here. Open a terminal. So if we do grep strings. So if we want to search for usernames, we want A to Z in caps, 0 to 9. We want a minimum of 6, so 6, max of 12. I guess we don't need numbers actually if it's saying filtering for users uses alphanumeric, so it is 0 to 9. Lowercase letters. Good, so that should be it. So we're actually getting a bunch of random shit in there as well. Great. So what if, instead of that, let's do, we want the start of the string, so let's put our caret and dollar in. That's better. So we've got 1, 2, 3, 4, 5, 6, 7, 8 that match that. So 8. Hey, what was the hint? This regex can be seen in one of the examples in the task marked one of the most foundational regex patterns, max and minimum used. Yeah, okay, that was easy enough. So filtering for usernames. One username consists of a readable word concatenated with a number. What is it? That looks like user35. Then filtering for emails. How many emails fit in the syntax above? So we're going to need... What was the syntax we've got? The local part is a random string, so that's going to be we could just do a dot, I guess. So anything /at, and I guess anything again. So and then /.com. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I did my quick maths, here we go. So yep, so we can use anything followed by plus to match random strings. To match the dot, we need to escape the dot, which is what we did. So how many unique domains are there? We've got Gmail, AMG, Yahoo, so another Gmail, 4 for Redfall, 5 for TryHackMe, another Yahoo, Canary 6, 7 Hotmail, another TryHackMe, another Alpha, to 8.
Herder of Cat says,
Done. White check mark. Smiley face.
Is that today's one? Congrats. So filtering for an email. What is the domain of the email with the local part Lewisham? So we need to find a Lewisham. So it's amg.com. Filtering for email again. What's the domain with the local part maximax? So that's redfull.com. Uh-oh, your answer is incorrect. Okay. Oh, fedfull, not redfull. I can't fucking read. There we go. Filtering for email. What's the local part of the email with the domain name hotmail.com? So that's Hussein Volt. Filtering for a URL. How many URLs fit the syntax? So we need to do URLs. So this time we're going to search for other highlighted things. So what's our syntax? So URLs start with either HTTP or S, so we can do like that, I guess. Let's double check. I can't remember what the thing is. HTTP, HTTPS. So if we search for just HTTPS, we're going to miss the first one. We need to make an optional S like that. So that's fine. And then some have www. Some don't. So if you think we've got so we're going to have this kind of structure, some with www, some without. So we need to do, I don't know if we have to escape that one, we'll probably do it like that. So we need to escape those. www needs to be grouped and optional. And then some URLs have W, and the TLD shouldn't exist. So we might have a, let's do a caret, and then the dollar. I don't know if we probably won't need that bit. Let's just see how far this gets us. So if we just do it like that. Should I put it in my clipboard? And paste. Brilliant. Go on, snap. Snap. Right, so the thing I'm going to do is... Oh, why is it doing weird stuff? Caret HTTP S optional. And we put our thing in www optional. full screen again. So we get some weird. There we go. Let's figure it out. So actually, the TLD doesn't look like it matters too much, so that's probably fine. So filtering for the URLs, how many URLs fit the provided syntax? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. No, okay, so... guess that one doesn't match it really. So it should be 16 if you ignore that one. Yeah. Yeah, because Schindler doesn't have a TLDR. Alright, so filtering for these URLs, how many start with HTTPS? I can just cheat by doing it again. So we'll do... take the optional off. And then we get 1, 2, 3, 4, 5, 6, 7. Cool. So if you feel like you could do with more fundamental skills in your life, try the Linux Fundamentals module. All rooms are free in that one. Cool. That was it. Yeah, easy. I've got a pretty good grasp of regex. So massively suggest trying out regex 101 if you haven't. It will definitely help with that task, as well as give you an explanation as to what's going on. So I reopen it. If it wants to load again, come on.
Web link.
So HTTP www. So this query that we wrote, the text string as the input. Here in the top right you get an explanation of what every single step of the regex is doing. It's like asserting positions, matching on certain characters, what groupings it's recognized.
Doing any boxes?
We might do. Depends what time. It's only 8 o'clock, so... and then you get some extra matching information, so it'll give you a bit more of a better explanation as to what's happening when you test these regexes. Right, all set for 18. This was a big wordy task today, so let's terminate my box so I don't try hack me shitloads of money to run a machine for 2 hours.